In this video, we're going to be showing you how to use the GROMACS Molecular Dynamics software directly on the Neurosnap platform to perform a molecular dynamic simulation of two proteins in a complex. Now, for those of you who aren't aware, Neurosnap is essentially an online web server where you can access a lot of different tools and models for research in molecular biology and chemistry. And in this particular video, we're going to be mostly talking about GROMACS as well as how to perform a molecular dynamic simulation without having to get into any technical steps such as programming or using a command line interface. So for this video, what we're going to do is we're actually going to build upon one of our last videos, which was the NeuroBind video where we designed some DARPins against PDL1. So this was a great video. NeuroBind is one of the models that we developed, and it's great at optimizing binders as well as creating new binders against a target with specific properties that we want. Now what we're going to do is we're just going to go ahead and download the rank 1 structure. I've already downloaded it, but you can see all the files that are produced from every single job over here through the Files tab. And then after that, what we're going to do is we're just going to type in PDL1 DARPin from NeuroBind. And this is more of a note that we're going to be writing to ourselves in the future just so we can stay organized. Now, the next step is going to be to upload the structure that we want to simulate. So in this case, it's going to be the rank 1 structure, which contains 2 chains and 377 residues in total. After we do that, we have a couple different options that we can play around with. One is to fix missing atoms. So sometimes when you get a structure from like the PDB structures can actually be suboptimal because they might be missing certain atoms or certain residues, or there might be other issues that need correction. So what this option does is essentially just uses PDB Fixer, and PDB Fixer is another tool that we offer on our website. So if you want, you can run that separately, or you can enable this option. In our case, because NeuroBind does a great job of filling in all the different atoms, we don't actually have to enable this for this particular job. The next step is going to be the simulation duration. So this is the number of nanoseconds that you want to actually perform the simulation for. Just as a warning, the longer your simulation, the more compute time and the more resources it's going to consume. So just make sure you budget for this accordingly. As you know, if you want to do something like a 300 nanosecond simulation, you can absolutely do this, but it does require a lot more compute time. Next up is going to be the simulation temperature. So the simulation temperature is measured in Kelvin. 300 degrees is very good for most use cases, but if you want to lower this or increase this, then all you have to do is adjust this number directly on the website. Additionally, the force fields that we offer a lot of different force fields. The default one, which is the amber 99SB ILDN force field, it seems to be very good for the vast majority of use cases, but if you know better force fields for your particular application, then you're more than welcome to change this. Next up is the solvent box. The solvent box is essentially the simulation box for which the actual simulation is contained within. So if we look at this screenshot, we actually defined a cubic solvent box within the system, and there are a couple different options. So for instance, you can do dodecahedron or something else, and the system will essentially be constrained so that everything fits within that container, if that makes sense. And additionally, there are other options as well, such as dodecahedron, triclinic, as well as octahedron. For most cases, cubic and dodecahedron are the optimal ones to choose from. Lastly, we have the ionic conditions. So in this section, we can essentially specify which cations and anions we want to specify, as well as what concentration we want them to be specified, and optionally which charge we want to specify for those ions as well. In most cases, you're probably going to want to use the default clinical conditions. So for instance, the current entry is already set to using sodium chloride at a concentration of 0.15 moles per liter, and the charges are just set to the default 1 and -1 for sodium and chlorine respectively. After that, what we can do is we can hit the run job button, and everything will process directly on the Neurosnap servers. And then once the results are prepared, you will get an email or a notification, and you'll be able to view everything directly on the platform. So we'll be back once everything's done running. We are now back with the results, and as we can see, this simulation took about 49 minutes to complete, which is fairly standard for a simulation of this size and duration. Now, the first thing we're going to be looking at is the actual resulting trajectory. As we can see, there are several different frames that we can iterate through, representing different time steps within the simulation. The first frame is going to correspond to the initial state of our system, and after the last one is going to represent the final state of our system. Now, a nice thing that you can do on our website is you can actually export the animation and animate it directly within the browser. So, for instance, we can set the duration to 25 seconds, and this will produce an output MP4 video of 25 seconds long that will iterate through all different frames. We can hit render, and this will show the animation over here, and then after that you can share it and so on and so on. Now, while we let this render, we're going to actually take a look at some of the other plots that are produced from this simulation. For most of the plots, what we want to look at is we want to look at consistency and not a whole lot of fluctuation. So for context, the first plot we're going to analyze is the RMSD plot. Now, this essentially represents the deviation in like the protein structure or the complex structure that you're simulating over time. So as we can see, there is a little bit of fluctuation initially, but it seems to kind of cool off a little bit, and we can also see where that deviation is mostly present in. So for instance, we see that the side chains appear to be the most variable, which is fairly standard. You'll definitely see that. And we can also see the deviation for the alpha carbons, the backbone, as well as the protein as a whole. The next plot we're going to be taking a look at is the RMSF. So the RMSF shows you the fluctuations in the positions of different residues throughout the entire simulation. So it's kind of like an average of the RMSD plot, but for specific positions within your structure. Now, if we were to analyze this one, we can see that between the positions of around 211 all the way up to 220, this particular section of the protein seems to be a little bit more fluctuating compared to, say, like, positions 250 to 300, which seem to be relatively still, aside from this minor spike. And even then, this isn't a particularly massive fluctuation either, so this could just be part of like a loop or something like that. Now, after that, what we want to do is we want to take a look at the radius of gyration. So overall, radius of gyration is a good way of measuring how compact the structure is. And if you're designing something like a peptide or maybe even like an enzyme, generally you do want more compactness, as more compact structures generally have more traits that are correlated with developability, but there are obviously exceptions to this as well. So for instance, if you're simulating an antibody bound to some kind of target structure, compactness might not be the greatest indicator. It just depends on the context, really. Next up, we have hydrogen bonds. So we can see that the hydrogen bonds are relatively still, maybe a slight decrease. And again, if we do a much larger time scale for the actual simulation, we'll probably have more data on that we can use to extrapolate a conclusion. So in most cases, you want to see an increase in hydrogen bonds, especially when you're dealing with like a complex. But if it's relatively still, like over here, that's not a bad thing either. Next up, we have the total solvent accessible surface area. So the total solvent accessible surface area, or SASA, essentially just tells you exactly what the plot is explaining. It's a surface area exposed to that protein structure. And we can also take a look at the per residue SASA, which essentially tells us throughout the entire simulation how much solvent exposure did like every single residue actually get exposed to, and you also have access to the standard deviation. So you can interpret that in a similar way to the RMSF plot over here with some nuances. Additionally, we have the DSSP secondary structure content over time. So for instance, if you want to know which positions had which secondary structures at which times, as well as, on average, which secondary structures were the most common, we can see that over here within this plot, as well as within this table over here that shows us the secondary structure assignment at various time steps. Lastly, we have the scatter plot that represents the minimum distance. So this just shows you the closest separation between periodic images. The best way to interpret this is to use it to find out whether or not the actual solvent box was sufficient for the simulation. So if you had issues with the solvent box, then usually you'll see maybe like some spikes over here at particular time steps. Though, there are a couple different ways that you can analyze this data and make use of it. We also perform equilibration during, to prepare the system. So we do NPT and NVT equilibration, and these over here are the resulting plots from those equilibration steps. Now you're going to notice that these have different time steps compared to the above, and that's because they're essentially completely separate steps. So don't worry, there's no issue or anything. This is a very expected thing to see. And additionally, in a lot of cases, especially if you take a structure from the from AlphaFold or something like that, and in some cases the PDB, you might see a massive spike in like pressure or potential energy or something like that. And this is absolutely expected because a lot of times, these structures, they might have minor defects that are present initially. So for instance, AlphaFold 2, it always messes up the side chains, and because of that, there's going to be steric clashes and whatnot. And because of those steric clashes, you're going to get energy readouts that are not going to be realistic. So that's quite normal, and you can always ignore those initial ones. Now, if they're happening further down in the simulation, that could be a problem, and you might have to reach out to us because there might be an issue with how the simulation proceeded, or perhaps you had a ligand that wasn't parameterized as well as it should have been. So if you do see spikes further on throughout the throughout these plots, then definitely reach out to us. Finally, we have the mmPBSA plots. So mmPBSA is essentially a technique that allows us to measure affinity, or at least try and calculate affinity in an approximate way. And there's a whole lot of data that you can go through over here. If you have ligands or different chains, then this will essentially report different terms and whatnot. We also have different terms for bond energy, angle energy, as well as all the other energies that we all love so much. Now, I hope you enjoyed this video. If you have any questions, then please feel free to reach out. And as always, we'll see you in the next one.